All right, good morning. We had spent a little bit of time on trace routes last time, and I want to kind of remind you how this thing works. What we do is we send a packet on purpose to a router that is on its last gasps. We can't really detect loops because routers don't remember the packets that they've seen before. Every packet is independent. It's just like a mailbox. You know, just because you get a letter in there today going somewhere, you may have had a letter in there before, you don't pay any attention to whether it's the same one or not. There's no state maintained. So in order to keep loops from happening, we keep count of how many times, how many routers the packet's been through. So every time a packet goes through a router, we deduct that number by 1. We store it back inside the packet, and it moves along to the next router, where the next router will deduct it by 1. And if everything's fine, it'll continue on. If the router ever gets it and it deducts it down to 0, then it assumes that there's something wrong. It drops the packet and sends a message back, an error message, all the way back to the original sender. So that's how we trick the router into disclosing its identity to us. Normally, you wouldn't see who the router is, but this is a guaranteed way to do it. Normally, with the program, with the specific program of traceroute, what traceroute is actually doing, and I'll grab it here, is it's using a protocol called ICMP Echo. Alright, so we can stop that and come over here and stop this. The problem's going to be there's so many frickin' 128, 42, 204, 44. 128, 42. There's so many packets. All right, so here we go. So these are the error messages that are coming back. And if I look at one of these, they're all UDP messages. We don't really know what that means yet. We haven't quite looked at that. But the problem is that the data I'm getting back is basically telling me that I've run out of space. So if I send one here, what I'm trying to find right off the top of my head is time to live 5. So when I sent this one out, I was trying to get the 5th router on the path. I don't know how many there are. Maybe there's only 4, but I'm going to try it. At some point, I'll get to one that is the destination itself, and it will respond. It will respond back. But in this case, I sent it, and it had 5 to go. Here's some other here. These had 4. You can see this number here in gray as I scroll up the packets. 3, 2, 1. Right. So this one is the packet that I got back when I asked the 1st, 2nd, 3rd, 4th router. Right, so that's what's going on. The problem is this is a very specific type of packet. It's known as an ICMP Echo. It's got a very particular format, and the routers now are onto us. They know what it is we're trying to do, so many of them ignore us because they both don't want us to waste their time responding to pings, and it's none of our business what they are. So when you run traceroute, or when you are trying to do something like traceroute on some machines, and you're trying to use Wireshark to grab them, you may not find any of these ICMP Echo packets, these ping packets, which is the normal default. So what the authors of traceroute have done recently in Windows and in Unix, for example, is they've used other types of packets, email packets, web pages, network time updates, FTP packets, any kind of packet. They all have this hop count, and they all must create an error when the hop count gets down to 0. Because it is a legitimate error, and routers cannot ignore it. So we've upped the game on them, and if you don't want to respond to pings, then try ignoring an HTTP packet, why don't you? And see how long that gets you. So just have fun playing with it a little bit if you want, but it's a game a little bit now because router administrators don't really want us to know kind of what's going on. The other thing I'll point out is that sometimes you get surprising answers back. So here's one I did to Microsoft.com. So you see it's a trace route to Microsoft. They have multiple IP addresses. So this one's going to go to that one. We'll explain later how do you know there's multiple IP addresses. So the first place I try to go is the U of H. I leave U of H. I get to Southeast Texas Gigapop. I get to Microsoft Network MSN. They have a POP in Houston, or they have a point of presence probably at an Internet Exchange Center. And then it gets backhauled someplace. I don't know what IBR or any of these letters mean. They're specific to the Microsoft Azure data centers. San Antonio is one of the big ones. My guess is that's where that one is. All right, so that's to Microsoft.com. Look what happens if I trace route to www.microsoft.com. It's a different computer, probably. You can have Microsoft.com set to respond to incoming web page requests if you want. That's perfectly fine. By default, you will usually teach Microsoft.com or any domain like that to at least forward an incoming web request to the right place, because it's the dominant use of the internet is going to a web page. But in this case, I specifically typed in this one, and you'll notice right at the very first line, I've been redirected to a place called Akamai Edge. So one of the things that has happened in the last 10 years is lots of large content distributors on the internet have stopped using the internet. They connect to the internet around the edge, very close to where the hosts are. The host systems just kind of hang off like fruit on a tree at the edge of the internet tree, but they don't use the internet itself to kind of get where they need to go. So they build a separate network, their very own, and they drop computers off of their network that hang off of the edge of theirs that connect to ISPs at the edge. So they're very, very close to you. They're like one hop away, but anything they need to get to you from their headquarters, they can do so over their own private network. They don't depend on the internet to do it. And the reason why this is done is because they can have a lot more control over the experience. They can prioritize traffic. They can send lots of data at once. They can guarantee no congestion, no drop packets. They can run circuits exactly where they want, minimize the number of hops, etc. So this is how the vast majority of file distribution is done. So whenever you go get a file from Microsoft, like download Windows, or you're trying to pull a large document off of a library site or something like that, it may very well be that it's coming from the server that is owned and operated by a company like Akamai, which is a content delivery network, a CDN, as it's called. There's lots of them. Google is a CDN. Microsoft is one. Akamai is one. Limelight, Level 3, they all do it. There's other reasons why they're useful that we'll see a little later on in the lecture. But this idea of putting a server that maybe sits inside of AT&T's ISP in Houston, and anybody that wants to get content from that company, the AT&T network loves it because they don't ever have to haul that traffic over their network. You've bothered to go ahead and just deliver it right in at the edge. So they don't even have to use any of their bandwidth to do it. But you can dump lots and lots of traffic on their access network in Houston. So there's one application that's the dominant example of a company that dumps tons of traffic using a content delivery network in every ISP around the world. Now, it used to be just in the US until a year ago. Now it's all over the world. And you guys all use it, probably. And the files are massive. And so the only reason this works really well for you is because you are not actually going over the internet to get there. Does anybody know who the company is? It's a website that you type in. I mean, it's a well-known name. You go here whenever, usually in the evening when you're at home. Netflix. It's exactly who it is. So Netflix doesn't have a data center. They don't really own very many computers. They have some that keep track of your password and your credit card number, and that's it. The files that they get from the movie studios have to be converted to lots of different sizes and formats and levels of compression. And so they use Amazon Web Services for that. And then they hand the files when they're done off to people like Level 3, Limelight, and Akamai. And they have them duke it out every month in every city to see who can deliver movies with the fewest interruptions, the fewest pauses, the fewest dropped packets, etc. So the problem with this is that companies that run these access networks are there minding their own business, and suddenly their network is just swamped. Netflix accounts for over 50% of internet traffic on access networks during prime time. It's just one application that's over half of the traffic. It's unbelievable. And so this is why companies that own these access networks are like, you show up, you don't pay me anything, you dump all this frickin' traffic on my local network, you congest the hell out of my routers, and you're telling me it's supposed to be, I should be happy to do that for you? Screw you. This is expensive for me. If you want to come and make your living off of my network, you need to pay me something for it. So that's basically the argument. Anybody know what that argument's called? So it's about whether you should allow traffic through at no cost, treat all traffic equal on local networks. Net neutrality. So should you prioritize some traffic over the other? Should ISPs be allowed to hold some of that stuff back? And their argument is, well, it's your business model. You told the user, sign up for internet. You can download whatever you want. There's no charge for doing it. I'm actually doing you a favor. At least I'm putting the server at the edge of your network. Otherwise, I'd clog the whole thing up all the way back into the internet. Excuse me for having a popular service. Maybe you should have come up with one. So there really are two sides to this argument. Very good arguments on both sides. Those are the best ones when they're hard to kind of figure out what to do. It's not like a David and Goliath story so much. So we'll talk during the semester about Netflix a lot because that's one that you guys all know, right? So that's why when I go to www.microsoft.com, they have paid Akamai to host a copy of their website and all these servers around the world. So that's why I'm only going to Akamai Edge. And as we see when we get to the security section later in the lecture, there's another really huge benefit that these guys play in mitigating attacks. But we'll get to that in just a few minutes. All right, so we'd already gone through these slides last time, and we're talking about how do you figure out what throughput is. Throughput is always a factor of the weakest link, of the smallest link on the network. However many hops you have, whichever one's the slowest one, that's the one that determines how much stuff you can get done. So for this reason, lots of the core backbone providers try to connect with each other with the same speed of networks. So at least if you're routing one way and you change your mind and route the other, you're at least not going to deal with connections that are different sizes. So this really is more of an issue at the edge of a network. This is a more realistic, typical example. 3 users trying to get to 3 servers. They share a link in the middle. And very often for a particular user, the connections at the edge are the bottleneck. But as we'll see a little later, we can do some things when we build web servers to keep this from being the big bottleneck. And we just talked about one, which is drop a copy of the website off over here on this side of that connection. And then it never has to go across this connection to get there. Okay, so we're going to take a look at layers today. Layers are ways of dividing up a software problem into independent pieces where one person doesn't have to know all of it and lose their mind. I will tell you there is healthy debate over whether layering still makes sense. And I think the line that we use is layering considered harmful. I've seen a senior network engineer at Cisco stand up in front of the presidency of a government. They had sent a bunch of people over to Cisco, and it was one of my customers. And they basically said, if you think you can get away without knowing everything that's going on top to bottom in the software, good luck. You're going to just get hacked constantly if you don't. So there's some arguments against doing this because the flip side of this is if you only focus on your layer of stuff, you're really putting too much trust in people on either side. And we do a bad job of managing security, so you should be suspicious of everyone at all times. You should assume people above and below you don't know how to do their job. That's the safe, prudent approach right now. It's paranoid, but it pays off. So what is layering? Layering is a good example shown by air travel. You've got various roles that you play you first interact with a ticketing agent, and then you check your baggage, you go to a gate, you get on a certain flight number, take off on a certain runway, and then air traffic control routes you around. So each one of these can be thought of as a layer with certain information, certain responsibilities. So the ticketing layer has to have the software to price tickets, to sell tickets, to collect money from you, to issue ticket numbers, which I'm going to call addresses for now. And so these tickets have to interact with baggage. You know, your bags have to be positively connected to somebody who's getting on the plane. So there is a relationship between the two. But the baggage numbers on your bag, the bag claim ticket number that you put on it, has nothing to do with the ticket number on your receipt. They're separate addresses. Furthermore, the gate numbers have nothing, of course, whatsoever to do with bag claim numbers or ticket numbers. So at each layer, you've got different responsibilities, and the person who's managing all of the gates probably doesn't know anything at all about tickets, and they don't really need to. They need to know a little about bags, though, because the bags need to show up at the gate to be loaded onto the plane, maybe like down below, right? And the same thing with the runway person. All they need to know is the flight number and what gate it's coming from, but they don't need to know anything about the bags or the tickets. And so you can kind of see how when you get down to the bottom, you work your way across the country from one air traffic control center to another. I don't know if you guys have ever heard of this app called Flight Aware. Have you ever seen this? I use it all the time because I'm flying, but it's also fun because I live with somebody who's very good at looking at planes in the sky and guessing where they're coming from and going to, which irritates the hell out of me. Okay, so let me show you what this looks like. So this is a live view of the flights coming to and from Intercontinental Airport. And if I tap on one of these, this flight is American Airlines flight, whatever, a Boeing 737-800 going from Intercontinental to Dallas. And if you click on the flight, you can get more information on it, and I don't exactly know how to do it, but they'll tell you what the route it's going to take, how far it's gone, its call sign. Then there's one in here that shows you every step along the way, its altitude, where it is, which air traffic control center. And I'm like, really? We can get access to this? I'm not breaking the law doing this. So it's a lot of fun, but it's a good example of how this layering scheme kind of works. So we do the same thing with networks. We have a big job to take packets from your application and get them out the bottom and through routers. And so we'll use the same idea of layering, and it gives us at least a reference model. And there's the layering considered harmful at the bottom of that slide, as you can see. So the idea is you can change what's happening in one layer without people on either side having to change what's in theirs. Think about a car. No matter what changes under the hood, it's still the same steering wheel, brake, and gas pedal that it has been for 100 years. So nothing much changes there. These are the 5 layers of the TCP/IP protocol stack. Physical data link, you'll rarely see it referred to as just link. For one thing, it screws up the mnemonic that we use to remember this. Network, transport, and application. So if you'll add data link to this, then it starts with a D, and you can have please do not take advice as your mnemonic. Now there's some filthy ones, and I do not want to hear them in this class. So, but you can go look if you're interested. And I'm trying to figure out if they exist in other languages, particularly Spanish. I haven't found one yet. So the application layer is at the top. That's where we run our programs. If I ask you what layer is software running at, this is almost all software. If you don't know that it's running in another layer, absolutely guess that it's an application layer protocol. You'll be right. So what about HTTP? What layer is that protocol running at? Do you know? So what are you going to guess? The top one. Guess application. So you'll be right 99% of the time. Almost everything you and I have access to in a system as regular users, where you can go to a command prompt and type it in and it runs, or you can double click on it, is almost always running in this layer. Now, you and I think of it as an application anyway because it's something that we installed on our computer, and that's not quite the same definition. What I'm talking about is where does it fit in the stack. Transport layer takes the packets from there. So there has to be a way for this software running in the transport layer to give you a mechanism to hand data. If you write an application and you want to send data out to the internet, there's a function call you make that's part of a library of calls called a socket library, and there's commands for different types of services that you can request. Some of them, for example, will work hard to make sure none of your packets get lost, and will retransmit them if they've discovered that they have. They'll work hard to give the other side the ability to reorder them in the correct order if they've gotten out of order during transmission. That happens. They'll give them the ability to detect duplicates. And then there's also versions of services that you can call with a different function call from your application that don't do any of that. That's just best efforts. You grab a packet and throw it on the network. So you pass to these function calls things like the address of the destination computer somewhere else on the internet and the data that you want it to take, like maybe a web page request or part of an email message, for example. Sometimes the network can't handle messages as big as you'd like and they get broken up into pieces. That all happens down in the lower layers of this software. And then network is where IP lives. These are where IP addresses are. So when a packet arrives at a router and the router's trying to decide, how do I get to Albuquerque? Do I turn left or do I turn right? Which link do I leave? Then the software that builds those tables and keeps track of where I can reach and where I can go and what destinations are available, those all run in the network layer. And so your routing protocols run in the network layer. Okay, that's what runs inside of routers. That's the most important task the router performs. And then the data link layer and the physical layer are usually conjoined because the physical layer is nothing without the definition of how to encode signals on it. So this would be Wi-Fi or Ethernet or a serial cable or some other type of wireless, for example, 4G, for example. Okay, 4G is really a little lower layer. It's more just physical. There's a competing, a superseding set of models. In the 40s, this organization, in 1947, the International Standards Organization was created. TCP/IP came along in the 60s, and by the 70s, the Standards Organization decided these guys are onto something with this layered model idea. So since there's more technology out there than just TCP/IP, why don't we come up with a model that will fit into, so we don't interfere with what they're doing, but try to give some guidance to other people that are trying to write. So of course they thought they could improve upon it, and they added two other layers, the session and presentation layer, which leads to please do not take salespeople's advice. So you can get a couple of other words in there. But, I'm really, really, really competitive, and I'm a sports complete maniac. And so I can't help but point out that they lost. TCP/IP won. How many people run OSI on their computer? No one? Anyone? No? Okay. That's my point. All right, so one of the concepts when you pass messages from your application down to the next layer of software using that function call that I mentioned is something called encapsulation. So the way this model works is really kind of curious. You hand everything you need to communicate to the application at the other end through this function call down one layer. The transport layer also may need to add some things. Remember, one of the options the transport layer can offer you is keeping track of packets out of order, retransmitting packets that got lost. So it's got some extra information that it needs to send along as well. Wasn't anything you put into your data, but it's something the transport layer needs. So instead of going in and messing around with your packet, what they'll do is something a little different. They'll take this message that you created and you pass down to the transport layer, and they'll leave it alone, completely intact, and they'll put whatever extra information they need on the front. So this would be like taking your stuff and putting it in an envelope and writing address, on the front of it. That in turn gets handed down to the IP layer, where the same thing happens. It treats everything it's been given, which you and I know is really this header plus the original message, but to the next layer down, it's just all the data that it was handed. And it needs to put some more stuff on. It will do so in its own header. So it's like putting it in another envelope. And this model will continue on until you get down to the physical layer. And the packet's getting bigger at every step, unless it's too big for the network and it got split up into pieces. But the idea generically is it's getting bigger at every step. At each step, nobody cares really about what's inside of here. They're just taking what they've been given from the layer above and adding what they need. You eventually get down to the Ethernet layer. I think I've drawn too many on here. Application Transport Network. Yeah, I drew one too many. So this is Ethernet, and Ethernet actually puts some error checking code at the end of the packet. So we'll talk about these in more detail this semester. But this idea is called encapsulation. So the way to think of it is, if I want to send a birthday card to a professor at University of Houston, Victoria. You know, we have a campus there, right? A couple hours away from Houston. So I drop it, I say Bob, and everybody knows who Bob is, and so I drop it into the secretary's little outbox thing up in the office. It's in an envelope already. It has an address on it. Bob. Bob's the address. And I tell her this is Bob at Victoria. She'll take it and put it in an inner office envelope, which is one of these weird brown envelopes that ties up with a string, and it's got like 100 rows where you can use it over and over and over and over. Usually has holes drilled through it so you can see if there's anything inside. And this is how we get mail around inside of large organizations everywhere on Earth. So she writes University of Houston, Victoria on there. Right? So she's put a different kind of an address and encapsulated my birthday card with her own envelope. Then it goes to the campus mail room. Somebody comes around once a day and picks up the mail. It gets over there. They grab all the things that are going to Victoria. Maybe there's 10 envelopes today. And they put them all together in a pouch. Because we have a private driver delivery service, Lone Star Delivery, that drives things back and forth every day to Victoria. So it's been encapsulated again into a pouch. In this case, it had 9 other envelopes. You wouldn't do that. You would do one by one here, but the idea is the same. Another way to think about it is you buy a box of cereal. It's encapsulated in a plastic bag, which is encapsulated in a cardboard box. You put it in a plastic bag from Walmart. You put it in the trunk of your car. Every step of that is encapsulation. So this is a very common, powerful way. So as you sort of step through this, you start with your message, you add a header at the transport layer, and you finally get it down to the bottom. You push it across to the next location, and in this case, it's a dumb device. It doesn't really care what IP addresses there are. It's just going to send everything it gets to the router. It's just there to keep the signal electrically strong, let's say. So it doesn't know how to run applications or do any of that stuff. And it gets it across to the router. The router has lots of links on it. Only 2 are shown in this diagram. But it goes up a little bit higher to kind of take a double check and go, okay, Albuquerque, left or right? Makes a decision. It goes out the bottom. It gets its way over. And you decapsulate it at the end. So this is how packets are sent, every single one, trillions of times an hour, all over the internet. Every device is constantly doing this. So if you have a router, and it's got 10 links, and this is a 1 megabit link, and this is some other type of technology that's 10 megabits per second, one of the things that the router's got to do is get rid of all those headers and get back down to the original message or back down to the IP datagram so it can move it to a different type of communications technology. This may be wireless. This may be wired. Electrically, they're not compatible with each other. So you're going to have to throw away the parts of your layers that were specific to this technology so that you can move it over to the other side and take this data and put it on some other type of transport mechanism. So that's one of the advantages. So again, that's an example of one of the layers changing and the other layers don't have to. You don't have to worry when you send a packet how many links, what technology, what speed, who made it, what kind of code it is it wireless or wired? You don't have to worry about any of that stuff. So that's this layering principle working really, really well for you. Does that make sense? All right, are you guys are hanging with me? Okay, because it's cold and early. I totally get that. All right, let's talk about some fun stuff. Hacking. So there's a burgeoning field of network security. Things have really changed a lot in the last few years. I'll mention a few things that are quite notable. One of them is there's now systems, since storage is so cheap. Remember we talked about Google, you can pull up 5-year-old email as fast as you can pull up email from yesterday. So it's obviously not sitting on a tape drive somewhere. It's all on spinning disk, ready at any moment for you. How in the world does Google afford that? How do they manage to keep all of your emails online forever without charging you anything? Advertising. They figured out the business model. So it's made storage free for them. So there are models that help push the cost of storage down to nothing. Google used to have signs up in their company that said, throw away nothing. I'm not sure that they're doing that anymore. They've gotten into a little trouble with that. But the point for network security is there are devices that will keep a copy of the header that gets added on to your packet at the network layer. They just grab that one header. There's a lot of good information in just that one thing. For every single packet going around on your network, they keep a copy of it forever. Every packet. There's millions and millions a day at any given company. So if you get hacked and you figure it out, one way to know what happened is to go backwards in time, and having those headers is really critical at helping you figure out what's going on. And so you should assume that every packet you send is being kept forever. Maybe not the entire packet, but at least where you're coming from and where you're going to, and at what time, and etc. And after all, if you're sitting in Starbucks and you're using Wireshark to sniff people's packets, and you have your suspicions about your roommate, and you just see the website they're going to, even if you don't see the exact content that they're looking at, that's usually enough, isn't it? I mean, it's like, just exactly what I thought. So if you just know the URL, so yep, so you have to be careful. This is why they tell you to use VPN when you're in public places. So you can also learn a lot about hackers by just having the packets as well. The internet was not originally designed with security. It says with much security now. It wasn't designed with any security in mind. And one of the founders, Vint Cerf, who along with Bob Kahn wrote TCP/IP, Vint is now president of the Internet Society, which is the overarching organization that is at the top. He's a little regretful sounding lately, and sort of seeing that what's the name of it? I screwed this up last night because I couldn't remember the name of it, but in Terminator 2, the network that took over was Skynet or something like that. Yeah. So, it's like turning into Skynet a little bit. People are using this to, like everything, it just turns to crap and people use it to attack each other all the time. So just like everything else we invent. So the original invention was hippie, and now we're trying to play catch up. So that's one thing, keeping all your packets. Another interesting thing is the only prayer you have of surviving anymore is to have an appliance at the edge of your network that is constantly in contact with a trusted resource that is sharing with you all of the other attack vectors that other people around the world are experiencing. So you learn about them in real time during the day. Attack vectors would be like overwhelming you with a certain type of packet, or trying to send you something with a certain value in a field that somebody discovered causes TCP to crash, or whatever it might be. And as soon as one device figures out they're being attacked, then it teaches all the other ones. So Cisco has a large security organization And I know about them the most because I worked there until I retired. But what they'll do is they have a bunch of security engineers that are constantly watching what's going on, and as soon as they figure out the fingerprint, the exact recipe, how to tell that a packet is an attack packet versus not, they teach all the other devices around the world. So they think about 40 billion attacks a day that way. You're constantly being attacked. So if you are wondering if you're being attacked and you're not really sure about virus code and all that, I guarantee you you're being attacked. It only takes a moment. So having the devices learn from each other in real time, kind of with AI types of models, you have zero chance of keeping up with it yourself. If you think you're going to log in and like set some rules up in your firewall and things, you have no prayer. It's all done automatically. So that's another interesting innovation. So how do you attack people? There's several different ways of doing it. One is to infect the system by putting software inside of a computer. You can either trick people to download something and then launch an attack from there to spread it, or take advantage of a known vulnerability in software like a worm. And either way, what you're trying to do is get the computer to do something that the user doesn't really recognize as is happening typically. So keyloggers are a good example. God forbid you should ever accidentally download one of those, because every keystroke you type gets recorded. It doesn't do you any good to have a VPN. It doesn't do you any good to have a hard password or to change it every day if when you type it in, somebody is capturing your keystrokes. They know what it is. So where this is all headed to there is multi-factor authentication, where then we also send you a code to your phone, etc. Passwords are terrible. They are a myth. They're much like the X-ray machine at the airport. If it makes you feel better about getting on the plane, good for you, right? Mission accomplished. But is it really guaranteeing anything? Not particularly. So if grabbing this stuff, putting it on your system, recording keystrokes, all of these things, those are all very real issues. There's another whole family of attack types, though, where you try to bring a server to its knees. And one of the most popular ones is a denial of service attack. The problem with a denial of service attack is it's hard to tell at first you're being attacked. What it looks like is that you're getting really busy, which, sounds positive, right? Like, oh, great, I'm getting lots of hits today. Until you realize it's so many that you can't keep up, and you gradually come to the realization, like, something's wrong here. We've never had this many hits. And it gets to be so overwhelming that you realize you're being attacked, but you can't tell who the attackers are. You can't sort the packets that are coming in from the legitimate requests from the others. So let's say you're NewYorkTimes.com, and suddenly you get 1 million NYTimes.com webpage requests in 5 minutes, when normally you would get 10,000. Your server can't handle it. Your authentic users are somewhere in that million. They're 10,000 or somewhere in there, and you are going to try to give them the web page, but most of them are illegitimate, and you can't tell who they are. So that's an issue with DDoS attacks. They're very effective, and they are 45 years old now. They've been around since the very beginning, and they attempt to prevent the legitimate use of an application. So the field is migrating really rapidly. I mentioned there's some interesting things going on. One of them is those companies like Akamai, the content delivery networks I mentioned, because they're hosting lots of people's data and they have servers all over the world, there's some mechanism that when you type in www.microsoft.com, that the ISP and the content delivery network, and basically the internet, have implemented that keeps you from really going to www.microsoft.com. And instead, you get diverted to Akamai. We saw that in the traceroute, right? We never really went back to Redmond, Washington, or wherever that master server is. So there's a clue for how to mitigate one of these attacks. If you are being swamped with denial of service attacks, then why not let Akamai absorbed them at their 3,000 servers around the world. And none of that traffic makes its way over the internet. And yeah, you still have this problem of your legitimate users not being able to get access to your data, but you try best you can, and they may have to reload. It may take longer than normal. And while that's going on, Akamai's security team is very quickly figuring out exactly what's different about these packets than the other ones that are coming in. Maybe they have a certain bit set, maybe they're all a certain length, maybe there's something unusual about them, and as soon as they figure it out, they push rules to all their machines to just ignore them, just to discard them. So you guys know GitHub? Have you heard of this site before for open source software? So they had an attack last year that at its peak was over a terabit per second of attack. That's a lot of data. They can't begin to handle that. They had a contract with Akamai for DDoS mitigation. So as soon as they realized what was going on, they hit like the big red button on their desk and the alarms go off, and Akamai steps in. They push out rules to the internet within a few moments that divert all of the people trying to get to GitHub instead to their local Akamai server. And they quickly figure out what the fingerprint is of these messages, push the rules out, and in 10 minutes, the attacker stops. It takes all the fun out of it. So the only way you can really survive a DDoS attack at first is just to have more servers than they can attack. You have to be bigger than them. So now, thanks to Amazon Web Services and Google and Microsoft and these content delivery networks, you can, for a moment anyway, if you need to, rent 50,000 servers to absorb the blow and put a stop to it. Things have shifted in the last couple of years. People are spending less time on doing this and more time on trying to attack actual applications themselves, instead of attacking other systems. Okay, so they've been around for a long time, but like I said at the end, 50% decrease in network layer attacks. Now what people are trying to do is app layer attacks. So there's hundreds of these things a week. There's some companies that have an attack that's launched many times a day. You go to lunch, you come back, you're being attacked. You go to dinner, you come back, you're being attacked. You go to breakfast, you come back, you're being attacked. It's just attack, attack, attack. Don't these people have anything better to do? No. Cybercrime as a service is a really interesting issue. There were sites, and there still are some, but some of them have been shut down. In fact, in the spectacular stroke of luck, one of them was shut down while I was giving a talk on this, and I had their website up, and basically the website went away, and like every international police organization you've ever heard of's page comes up and says, this site has been confiscated. And so these sites would do things like somewhat legitimately offer stress testing of your network. We have servers around the world, and we can launch a fake attack on your site to see if you can withstand it. Are you able to spot it? Are you able to mitigate it? How's your mitigation service really working out for you, etc.? You can pay them with a credit card, PayPal, Bitcoin, but it's somewhat legitimate if they're taking credit cards. So for 25 bucks, you can have somebody try to attack you or attack your competitor. And that's the problem. So this was basically cybercrime for hire. For 20 bucks, you piss me off, you're going down. I can pay somebody to just swamp your site, and I don't have to lift a finger. So these are very illegal, and they're being shut off as they find them, but is a genius idea. It's just, as usual, another illegitimate idea that doesn't last. Okay, so software running in devices. One of the issues is these Internet of Things devices, the little bitty kind of components that are running in refrigerators and in vending machines and washing machines and things like that. And the problem with networking considered harmful is that people ignore, they just assume if they're buying like a Raspberry Pi, that whoever wrote the version of Linux that you're getting is tough. It's good. And the issue is your IT department, they'll absolutely keep track of the laptops in the organization, and they will insist that they have current virus patches, or they may not even let you use an operating system like that. They may centralize it and just have you use a program like Citrix to remotely control a server somewhere. Lots of companies do that. But they don't pay any attention to these Internet of Things devices. Well, they're full-blown computers. They have network access. They're running Unix. They have Bluetooth or Ethernet or Wi-Fi. And you can hack them. And one of the biggest attacks last year was just from a measly 100,000 IoT devices. Usually it takes 1 million computers. So you'll get people to download things, you'll get people to click on things, and what it does is installs a little piece of software, and it periodically checks to see if there's instructions by going to a specific site on the network and see, do you have orders for me? I'm checking in. It's like a secret spy. And you can decide, okay, Wednesday morning at 8 a.m., Greenwich Mean Time, I want you to start making web page requests of the New York Times. And however many systems there are, 100,000, 200,000, they all wake up that are turned on. They don't have any control over that. If your system's turned on, then everybody starts making web page requests. Doesn't require starting your browser up. Okay, that's for you. The browser page is what you look at. But you can make a function call from a program that's just running in the background to a socket library and cause a packet to leave your computer without you ever doing anything. In fact, that happens constantly. To check the time, to look at your location, all kinds of stuff like that. Okay. 3 categories: denial of service saturating the network, overwhelming the software, or attacking the hardware. The hardware attacks are new and really, really dangerous. So the hardware attacks are ones where they figure out how to go into reprogrammable chips inside your system, EEPROMs, electrically erasable PROMs, things like that, firmware, and wreck it. And if you wreck the firmware on a system, the only solution is to replace the system. So it's a permanent destruction hack. It will destroy the system and render it totally useless. Your only choice is to remove it and replace it. So those are extremely sensitive and a cause for lots of alarm. But one of the things you don't want to do is put lots of backdoors in your systems that allow people to change the firmware. So for example, you guys, have you taken operating systems yet? Some of you have? Okay, so when the operating system fires up, one of the things the system does when it first boots up is it goes to firmware, goes to ROM, and figures out, what am I supposed to do first? Where am I supposed to find this operating system? So there's something that tells it, go to this particular track on the storage device, the boot track, and load whatever program you find there. That's how your system either loads Windows or Linux or Mac or something else. Well, if you change that firmware and say, no, don't go there, go here instead, well, there's not going to be an operating system there. So your system will never boot again. If you can't even get the system to boot, how are you going to fix the problem if it won't even load an operating system? So these are kind of dangerous. Lots and lots of software protocols that people figured out how to attack. These are ones that we all use that were not written to be bulletproof, and people have found vulnerabilities in them. DNS is one that has become a popular target. Lots of big ISPs use this directory service, and we'll learn about DNS later in the semester, but DNS is like a telephone directory. You type in Microsoft, well, a router doesn't know what Microsoft means. It needs a number. It needs an address. So there's a directory service that connects between the two, and lots of ISPs don't run their own. They go to a third-party DNS server, a service provider, and they just feed them what they need to know. So one way to bring the internet down is to go attack them. If you attack them, then no DNS from them and no DNS for the ISPs, and so this is what brought a third of the internet to its knees a couple of years ago. So this stuff happens on a pretty regular basis. All right, so here's a direct attack. That's stupid. We know who you are. We can come find you and put you in jail. Then there's a botnet attack where we infect a lot of compromised systems and then they in turn gang up on the poor target. That's a little easier to disguise who you are. And one of them that's extremely effective lately is called an amplification attack. So this would be like sending a packet on the internet that says you asked for a web page to be delivered from a site where the web page is like really, really big. So I send just like 8, 10, 20, 30, 40, 50 bytes. Doesn't take much bandwidth for me. Don't need a very big system to do that. And what comes back is hundreds of thousands of bytes. So if I can send a packet out and sort of convince you that it wasn't me who requested it, even though the packet came from me, but it was him who requested it, I can send 50 bytes out and cause you to get hundreds of thousands of bytes headed your way. So it amplifies the amount of traffic that I'm able to send that comes back towards you. And so that's a very effective attack as well. So here's the memcache attack on GitHub. At its peak, it was 1.35 terabits in size, and this was at 5:26 p.m. By 5:35, it was over. That's a miracle. This is like a poster child for how it ought to be done, because they had a mitigation provider that stepped in and said, "Is that all you got?" You know, it's like your big brother that steps in and says, "How much to dance with your dates?" Right? Remember that from Animal House? So the amplification attack focused on 100,000 web caching servers. It was not a botnet. This was an amplification attack. A small series of requests were sent, 8 or 10 a second. And what happened was you got a 50 times return. So this is an example of sending out a little and getting, you don't even have to send out very many. You just get tons more data coming at GitHub. Within 10 minutes, they engage their DDoS mitigation service, part of Akamai, and game over. So a little bit more on that. Increasingly, nation-state players are doing this. There is government-endorsed attacking. Just before you think that we're all beat up, we do it too. We're pretty good at it. Here's one of the sites, Booter, that for $23.99, they would send 220 gig worth of attack traffic wherever you wanted. That's pretty good. Oh, and they'll support 24/7 support though, which is like funny as hell. Botnet attacker locations, as you can see, were there. The super vast majority of these come from China. And it's more of a statement of, I think, China not managing its networks well than it is China deciding it wants to attack everybody. So the attacks happen inside your own country as well. You know, this kind of backfires on you. So attack duration, most of them are less than 30 minutes now, which is crazy. Okay, one company had 242 attacks. Can you believe that? You must have really ticked people off. Another thing you can do to mitigate these attacks is put your hardware in a more intelligent arrangement. So one company that was being attacked just simply moved the device that was really good at dealing with it up to the front of their network. And if you put your firewall in the middle of your network, the attacks have to get through all the stuff at the front until it gets to the firewall and then it stops. But these devices are done. So you can rearrange how you put things and put it up at the front. You know, put the bouncer at the curb, not in after you paid to come in the club. You put them out at the edge, for example. Okay, there's more in here than we need on this because this came out of a TAC talk that I gave. So this is basically the idea. You can infect machines and have them gang up on somebody else. You also can sniff packets, and we talked about that with Wireshark. This is one where you can just listen for what's going on, but you can also take on someone else's identity and masquerade as them. And that's a very useful attack. So masquerading attack is one where you are closer, well, you're in between the source and destination. And so, of course, in either direction, the packet reaches you before it reaches the other end. So if I'm trying to talk to him and somebody's standing in between us, you're going to hear what I'm saying to him before he does, and you're going to hear what he's saying to me before I hear it. So think about it. If you go over to the University of Houston Center, the Student Center, and you walk in and there are people wearing tuxedos and they're taking orders at your table. And they're like, it's a special Hilton hospitality class final, and we're going to wait on you guys today. Isn't that cool? So here's McDonald's menu. Let me know what you would like, and I will go order it for you. And so you think they are, for all practical purposes, McDonald's. They're able to go and get whatever you want. McDonald's thinks they're the customer because they're showing up like a customer would at the McDonald's counter and getting food and placing an order. The problem is you give them your credit card and they're stealing the number. So the transaction still happens, but you've got somebody masquerading in the middle, and so that's a threat on the internet as well. That's an attack vector also. And you guys have played with Wireshark, so you kind of see how that works. So IP spoofing is sending things with a fake address. You can answer before the real destination can and convince someone. So for example, in the morning you turn your computer on. One of the things you need is an IP address. So you send out a special type of packet that says, is there anyone out here that's running DHCP that can give me an IP address? Well, normally the router answers, and they trust that no one else will try to convince you that they're it. But there's no reason in the world why you can't respond also. You go, no, ignore the man behind the curtain. I've spoken on the great and powerful Oz. Here's the IP address I want you to use. Here's the router that I want you to try to send things through. And you can convince them to send the packets through you that way. There have been attacks before where somebody just gets on a Wi-Fi network from the parking lot using a Pringles can as a Wi-Fi antenna. You can extend the range and connect to somebody's network and then send packets that advertise that you are the best route to get to everything else on the internet. And without even touching any of the other systems, they will all start trying to send traffic through you because they respond to those types of messages. Oh, okay, there's another route out to the internet. Okay, and you get to see all the packets that they're sending. You may not be able to decipher what's inside of them. Hopefully they're encrypted, but you can at least see where they're going and how many, etc. You can learn about how many computers there are, which ones are the servers, which ones are the clients. Very often you can tell what operating system they're running because the types of packets have different peculiarities depending on who wrote the code, etc. Okay, so early packet switching. We've talked a little bit about some of this stuff before, but have we talked about ARPA? Do you guys remember that? Advanced Research Projects Agency. Have we talked about the origins of the internet yet much? Sometimes I like talk about it on an early lecture if I get excited about it. So, like a lot of technologies, we have the Cold War between the United States and the Soviet Union to thank for the internet, because the internet was designed originally as a network for the United States Department of Defense as a way to add resiliency to what was a very vulnerable communications network. So the idea in the way communications networks used to work is you'd have devices. Let's say you're an airline, you're American Airlines, and you have ticket offices around the country. You each have one of these old IBM green mainframe green screens, we used to call them, and you have a dedicated phone line that attaches. It's not even really a phone line because you're not really dialing a telephone number. It's a different type of circuit, but it's permanent, right? It's just like a long cable, maybe 1,000 miles long, but it's a long cable. And then here's your mainframe computer in Dallas, let's say. So this is okay. If something happens to this device, then everybody's out. All right, so protect the heck out of this. But if something happens to this or this, there's these sites are isolated. There's no way to get to them anymore. So imagine this is Omaha, Nebraska, and a place called Looking Glass, where we launched the nuclear missiles. And these are all the missile silos around the United States. And if the Russians are attacking and you want to be able to hit the button back, if these things are torn up, blasted out of oblivion or whatever, you have no way of launching your missiles anymore. So the Department of Defense didn't like that, and they asked a guy named Paul Barron at the RAND Corporation, which is basically a company that gets hard problems from the military to try to solve, to come up with a scheme to get around this. So he came up with this idea of breaking information into packets. He didn't call it packets at the time. That word came from the UK later. But they came up with this idea of breaking information into chunks and giving each chunk an address. So he basically modeled the postal system. If you have an encyclopedia that you want to mail to someone else, you can take a few pages of the encyclopedia out at a time and put them in an envelope and dump the envelopes in the mail. And so as you know intuitively, if you drop them all in, they may not all take the same route to get to the destination. Some of them may show up a day later than the other ones because they're individually being routed by the points along the way. So the idea was you interconnect these things somehow into more of a mesh, and if one of these things goes down, then some device will just try a different way. And even though this has never seen a packet from here before, it's got an address, it has a pretty good guess as to where to send it next. So each packet was completely able to stand on its own with all the addressing information you would ever need. So that was a huge breakthrough in network design, and the Advanced Research Projects Agency, or ARPA, created this network called ARPANET that got early researchers on there, and it had 15 nodes after a little while. Then Vint Cerf and Bob Kahn wrote a successor to some of the early protocols because they wanted to do things like, well, what happens if not everybody has the same speed of link? And what happens if all these devices weren't made by the same person? And so the software is not going to be the same in all of them. I mean, it's like IBM against the world. Nobody's going to want IBM standard to win because they're like big and strong already. And IBM certainly doesn't want somebody else's standard to win because they like being big and strong. So we need to design something new that's like neutral, that everyone can agree to. So they built TCP/IP and put it forward, and eventually it became the dominant standard. But for a long time, the other equipment manufacturers did not support it. And then they finally had to, because the customers wanted them there. There were lots of other technologies out there besides TCP/IP, but Bob Kahn's an interesting guy to listen to. And we'll take a peek at a couple of these technologies as we go further on in the semester. In particular, AlohaNet, which of course is from Hawaii. And, you know, so it's got an interesting little, I won't wear a grass skirt and coconut bra, probably. Depends on how awake you guys seem. I may have one in my bag, so I'm just warning you. All right, so AlohaNet came up with some other really important ideas that kind of inspired Ethernet, which was a huge factor pushing things forward. By the 80s, we had hundreds of thousands of people on there. I very much remember having the very distinct impression and telling friends, this is going to be huge. Lots of times you can't spot things coming that are just going to be explosive, and you're like, oh wow, that really took off. But this is one where I said, this is going to be gigantic. So I was fortunate enough, I bought stock in Netscape the day it went public, which was the first internet stock that went out there, and was smart enough to sell it a few months later. so before it tanked. Okay, so there's a little more in history there. We're not going to spend a bunch of time on that. We don't really need to. What I do want to do is get us a little further along. Okay, so we'll spend maybe 8 or 9 minutes going through as much of this as we can. We may be able to get through the whole thing. So the idea behind applications is you've got to give programmers a very easy way of building a message that they would like to send to their peer. And you remember the airline example with the tickets and the bags? Those lines were all horizontal. So applications talk to other applications. They don't talk to other layers. You know, the ticket person doesn't go down and talk to the gate guy about gate numbers. The person scheduling runways doesn't care at all about baggage numbers. So the communication in this layered model is between the same layer end to end across two machines. The only time you talk to a layer other than your own is when you're inside of a computer. You can talk to the layer below or above, but only within a system. When you send a message out as an application, like a web browser sends out a message to download a web page, uh.edu for example, that message is intended for the web server, another application at the other end. The transport layer gets involved. It talks to its partner, the other transport layer. The network layer talks to only the network layer as you go along. So we'll take a peek at how we implement this client-server paradigm using this application idea, and we'll learn about some popular applications that you guys may not know the protocol names of, but which you certainly know what the applications are. So these are all examples of applications, including Netflix, but point-to-point sharing, remote logins, telnet, secure shell, text messaging, HTTP, email, Skype, WebEx, social networking, all those are application layer protocols, and they all use the same socket library that's been ported to every machine on Earth now, I think. And so you can sit down with Java or Python or C or Fortran or whatever language you want, and you will find there is a library of commands to send things out to the internet and to get things from. So it's a very simple set of commands, and you will have a chance to try writing some lines of code this semester just to get your feet wet. It's not hard. Right? There's like 4 function calls, and that's it. And so that's another secret to the success. So what you want to do is write programs that run on different end systems. That's the key. So the network is going to create the illusion that the other end is local to you, when in fact we know it's not. You don't ever need to write any software for any of the core devices. And this is a pretty powerful model. You can send a packet from your computer right now to an address that no router in this part of the world has ever delivered a packet to before. And they'll all know exactly where to send it. You can drop an envelope in the mail going to some place that no Houston post office worker has ever delivered an email or ever delivered an envelope to before in some other strange part of the world, and they know what to do with it. You can pick up your phone and dial a telephone number for some country on Earth that no one in Houston's ever called before, and the telephone switch is going to know exactly what to do with it. So this mechanism of this independent addressing and having a hierarchy is very effective and works great. So there's several different structures of programs. Client server is the one we use the most. Almost always you're connecting to, you are the client and you're connecting to some server. So this would be WhatsApp, for example. This would be email. You connect to the email server. All websites are this way. Dropbox is this way. You're connecting to the Dropbox server out there on the network someplace, and so forth. But there's also peer-to-peer networks as well that you use to download BitTorrent and things like that that are a little bit different. So the server is usually in a higher-end data center. It's usually on all the time. The difference between a server and a client, as far as we care, is when the server turns on in the morning, the call that it makes to the socket library is twofold. First, it says, I'm here, I'm awake, and I'm listening for connections coming in on this address. And I'm ready to take data now. So they wake up in the morning, they have no idea if they're going to ever see traffic, but if you write a piece of server code, you must initiate listening, and then you wait. Then wait and wait until somebody tries to connect to you. If the server's not up and running, when the client tries to reach you, the connection will be refused. It's not going to wake it up going, hey, wake up, you've got business. It's not going to work that way. If you're not up and running and listening, then the operating system will not recognize you as being available, and the connection will be refused. So if you've ever tried to connect to a site and you've gotten an error message that, site unreachable, we'll see some of those error codes. Some of them may, you may recognize, oh, okay, I've seen that number before, and that's what's going on. Okay, it's also been used as insults before. So if you've ever tried bringing up a web page and the web page doesn't exist, do you guys know what error number you get? Anybody remember? Anybody notice that? Anybody seen 404? Yeah, so we use that as an insult to somebody who's like not right quite there. She's 404, man, or he's 404, or something like that. So you'll hear us use things like that. P2P is different in that it's self-scaling architecture. You're not all ganging up on one server. You are distributing the load. This is why mitigation services work. You're turning a client-server model temporarily into a P2P model by massively magnifying the number of servers that are out there to help you deal with the attack, for example. That makes sense, right? And then what's really going on at the high level is we have Unix-based processes that are talking to each other. So this is simply like what you can do within a Unix system, but now we're inserting the network. So we needed these function calls to be somewhat like what remote procedure calls had been for years before. So programmers conceptually have no problem at all taking to this. It's easy. You will take a look at this and you'll go, okay, I totally get that. This is not going to be difficult code or difficult function calls for you. Thank goodness. I mean, so it's really easy to write code to do this stuff. Okay, we're at a good stopping point for now, and I will continue to speed up more and more, and maybe ask some of your friends in the computer architecture class if they did the homework for you, because I published your homework to them last night. But in my defense, I was like delirious and was on like 3 different medicines from my doctor, and one of them had codeine. I've never had that before. Let me tell you, I had the most vivid dreams I've had in years and years last night. I don't think I liked it because it involved losing my iPhone. And I was chasing the guy, and he was a doctor and a specialist, and like I knew who he was, and I was like, why do I have these dreams? So I woke up and I was like reaching for my phone. It's like, oh. So anyway, I posted the wrong homework. So anyway, if you have friends in architecture, maybe they have done the homework for you. I doubt it. All right, guys. Have a great one. Straight week. Yeah. Codeine dreaming. Yeah, I've never had it before. All right, bye, guys.